Hello everyone, I am Shubham, a third year BTech Engineering Physics student of IIT Roorkee. Today we will discuss about transfer function. I hope you all know what is the conventional definition of transfer function, and even if you don't know, let me tell you what it is. Transfer function is the ratio of Laplace transform of output to the Laplace transform of input when all the initial conditions are assumed to be 0. And here we have the mathematical expression for transfer function. Here capital Y, it is the Laplace transform of output, and capital X is the Laplace transform of input. And I think just after reading this definition, you don't understand what exactly transfer function is and why do we need it. To understand this, first we need to look at what impulse response is. So let's see what impulse response is, and after that we will be able to understand what transfer function exactly is. So let's go. To understand impulse response, let's take a real life example in which we have a block of mass m sitting on a table, and we hit this block by a hammer, and due to this hitting the block will acquire a velocity v naught, and due to friction after some time it will get slowed down and eventually it will come to rest. And this v versus time plot, it will look something like this. Now in this case we can think of this hitting as an impulse. Why? Because we are imparting a lot of force in a short span of time, so we can consider this as an impulse, and this velocity, it will be like impulse response. This is the response which this block shows after getting hit by this hammer. So now we have understood how this block will respond after getting hit by this after getting one impulse. Now let's see how the impulse response will look like if we hit this block multiple times with hammer. In this case we will record the response each time, and to find the total response we have to sum all the individual impulse responses like this, and then we get the total impulse response like this. Now let's try to apply this concept into LTI system. Here we have an impulse, and we are giving this impulse to our LTI system, and LTI system is responding by giving this response. In this way we have understood that given an impulse how system will behave, but we still don't know how our system will behave if instead of an impulse we give it an arbitrary input like this, a continuous input, because in real life we don't give impulse to LTI system. Usually a system is random, arbitrary, a signal is arbitrary, and it can be something like this. So to find out output of LTI system, what we can do is that we can break this input into infinite impulses. So after doing that we can record the response of each impulse, and to find the uh, total response we can sum these infinite responses. And but you know that they to do the summation of infinite values at a single time, it is quite impossible. So to overcome that, what mathematicians come with is this convolution, this concept of convolution. To give you a brief idea of convolution, let me tell you what is the I mean how this convolution happens. to understand it visually, we have two functions f and g. To find the convolution, we have to shift one of the function, let's say g, across the f, and in doing so the value of output is the area under the input function when they overlap, like this it is shown here, and the mathematical expression is given here, and the convolution of f and g is given by this integral. So whenever we have to find the convolution, we have to solve this integral. Now after understanding this concept, we know that whenever we have to find the output of LTI system, we have to find the convolution of input and the impulse response. Now let's see the definition again and try to understand transfer function this time. Now transfer function, as I have already explained, it is the ratio of Laplace transform of output to the Laplace transform of input when all the initial conditions are assumed to be 0. You see, I have highlighted this part because this condition is very important. Why? Because we find transfer function for LTI systems, and if initial conditions are not assumed to be 0, if they are not 0, then our system will not be linear, and in that case it will not be LTI. That's why this condition is very important. So we can find transfer function only when this condition is satisfied. Now let's say we are giving xt as our input into the system, having a impulse response st. Now to find our output, we know what we have to do. We have to find the convolution of x and t and h. Now we also know the formula to calculate that. It is given by this integral. Now here comes the beauty of Laplace transform. What we can do is that we can take the Laplace transform of both sides and see that this yt, it will get converted into capital Ys, and this whole integral, it will get converted into this multiplicative term. Now I am not going into the derivation part. You can find its derivation from any other source, but for the time being, let's say that this integral will get converted into this multiplicative part. Now what happens is, now we have found the expression for transfer function from this equation. Now this hs is the transfer function. Now we have understood what transfer function is, and now can we apply or can we understand the behavior of the system using this transfer function? And fortunately the answer is yes. We can find out whether our system is stable or not by analyzing our transfer function. So let's move ahead and see what is the stability. Stability is defined as the ability of a system to provide a bounded output when a bounded input is applied to it. So how do we find whether our system is stable or not? To find that, we have to first look at poles and zeros. Poles of a transfer functions are the values of s at which the denominator of transfer function becomes 0, and the zeros of transfer function are the values of s at which the numerator of transfer function becomes 0. And just by following these two definitions, we can come up with a general form of transfer function like this. Here z1, z2, z3 up to zn, these are all zeros, and p1, p2, p3 are poles. So because when s value of s will be equal to z1 or z2 or z3 up to zn, the value of transfer function will be 0, and when s is equals to s p1, p2, p3 etc., the value our transfer function will be infinite. So to understand it visually, let's look at a 3D visualization of zeros and poles. It is a plot of transfer function, 3D plot, and all these spikes you can see here, these are the poles at which the value of transfer function approaches to infinity, and all these downside spikes or downside hills structure, these are zeros uh, at which the value of transfer function is 0. Now let's see what are the stability condition. This is our S plane, and this is the left half plane, and this is the right half plane. So if all the poles, if they lie in left half plane, then our system is said to be stable. On the contrary, if they lie in the right half plane, then our system is said to be unstable. And if poles lie on this axis, imaginary axis, then our system will be called marginally stable. Let's understand this with an example. Let's say our transfer function gs is given by this expression, and the values abc are also given. Then, as I said earlier, in order to find poles, we have to equate this denominator to 0, and after doing so, we will find that the value of s will be -3, so the pole is -3. And if we locate this pole on our graph, we will find that it lies here in the left half plane. It means that our system is stable. Had this pole lied on right half plane, it would have been unstable. Our system would have been unstable. So I think I was able to make you understand what is the how can we analyze our system using transfer function. These are the references which I have used in this presentation, and thank you.